Hello, I'm Ben Vaughn, and today I'm going to talk about my Fundamentals 1 oral final. So for this final, I have two different questions. Without further ado, let's get started. So my first question is on thermal I'm not going to read this out loud. If you want to read the full question, you can pause the video. So what is thermal? The mechanism behind thermal bremsstrahlung is that we have an electron here in green passing by a group of positively charged ions. And as the electron gets closer to them, it gets attracted through Coulomb attraction and its path gets deflected. And this deflection in its path causes a change of acceleration in the electron, thereby creating electromagnetic radiation. That's thermal bremsstrahlung. Here, this path is greatly exaggerated. The deflection in reality is only really small. And so here's a much more physically realistic model. Here I have Z, which is the atomic number. So it's like if we have helium, we have 2 ions, or 2 times the electric charge for our ion. Here again, we have the electron. B is our impact parameter, and that's the distance of closest approach for this electron with this clump of ions. VT is the distance traveled by the electron after passing the impact parameter. R is, again, the total distance from the group of positively charged ions to the electron. And so these 4 things kind of parameterize how we're going to handle this model. Up here in the top, we have the Lamar formula, and there's actually a typo here. There should be D double dotted of omega, but here we have C squared. So this is, again, energy per unit frequency. And so we have omega to the 4th, and we have C squared here. This is the dipole moment. And so we can actually express the dipole moment as a function of time as the product of the charge and acceleration. And in order to get to this d omega, or rather to convert d omega to d of t, we need to take the Fourier transform. And so when we take the Fourier transform, we get out this for our energy per unit frequency equation. We can then use the Coulomb attraction law to calculate the acceleration of our electron, and then integrate that to find the change in velocity. And when we put all of those pieces together, we get out a change in energy per unit frequency as 8 times the atomic number squared times the electron charge to the 6 over the speed of light cubed times the mass of the electron squared times the velocity squared times the impact parameter squared. And so I have this bullet point here, and that's basically why 2 interacting electrons could not create a Bremsstrahlung spectrum, is because if we had 2 electrons, that would give us a net dipole moment of 0. And so we can very clearly see in this equation here that energy per unit frequency would just be 0. And so we have no radiation outward. So moving on, let us now consider a cylindrical volume of electrons that are incident on a clump of ions that are in the center of this circle here. And so what we're actually going to do is we're going to consider rings of electrons and integrate them out. And so we have here a number of electrons passing through this differential area of this ring. So we have number density of ions, number density of electrons, velocity, impact parameter. And we can rewrite this as energy per unit frequency incident on this ring. And so simply that just gives us this. We want to integrate over the impact parameter here. And so how do you actually parameterize the integrand? Like, what do you use for the lower limit and what do you use for the upper limit? For the maximum, for the upper limit, we use V times this scale parameter called tau. And for the lower limit, we use the Heisenberg uncertainty principle. And so when we actually integrate that out, we get this equation here, which is energy per unit frequency, per unit volume, per unit time, as this huge thing here. Most of these variables we already know, I've been over them, but GFF is new, and that's the Gaunt factor for free electrons, which is what we call thermal Bremsstrahlung radiation. It's called free. And that's just due to quantum mechanical effects that change the problem slightly. Moving on again, we actually want to get a spectrum. And so to get a spectrum, we have to consider that there is a dispersion of velocities for these electrons. They don't all just have the same velocity going around. And so we want to find an expectation value of that. And so we start by saying, okay, well, these velocities have a Maxwell-Boltzmann distribution. That's essentially just a normal distribution. And since there's 3 dimensions, x, y, and z, there's 3 different ways we can look at the velocity. So we're going to consider spherical shells. And so that's what this 4 pi v squared is about. Basically, we can find the expectation value by taking a weighted average. And so that's what we're doing here. This is literally just a formula for a weighted average. Here's our equation that we just calculated on the previous slide. And this is v squared here. For the 4 pi's end up canceling out. And that gives us this equation. And this is in CGS units, but we have atomic number density of ions and electrons, temperature, the Planck constant times frequency over kT times, again, Argon factor. And so we can plot those on a spectrum. Here they are. Here's a bunch of different temperatures. So 10 to the 9 Kelvin here and 10 to the 5 Kelvin in blue, and then some in between. These black dotted lines show the knee frequency, and that knee frequency is when this h nu factor is equal to kT here. And so that kind of says a turnover point where this exponential starts really dominating the equation, and it really drops down, and we can see that like drops way down. One of the nice things about the Bremsstrahlung spectrum is it is smooth. We don't have any emission lines or anything like that muddying up the spectrum. So that's nice. What can we use it for, though? So one thing we can use it for is galaxy clusters. And pictured here is a image of the Perseus cluster. In blue, we have Chandra in X-ray and Hubble in pink. So galaxy clusters have this hot gas that permeates through their atmosphere called the intracluster medium. And that's typically at temperatures of 10 to the 7, 10 to the 8 Kelvin. That's why we observe it in the X-ray. And when we observe it in the X-ray, we can get a thermal Bremsstrahlung spectrum, and we can use that to find the temperature, because we don't actually know what the temperature is until we measure it, and also find the density of ions for the intracluster medium. And that's very helpful because that can help us get at things like the overall mass of the cluster. And that's very nice to have for cosmology. The other thing we can use it for is H2 regions. And so here we have the Rosette Nebula. And for H2 regions, they aren't at a very high temperature. They're at 10 to the 4 Kelvin. But if we go back to our graphs here, we can see, oh, well, there still is a spectrum at 10 to the 4 Kelvin. We just have to look at it instead in the radio. And so we can take radio measurements of the thermal Bremsstrahlung spectrum. And again, do the same thing. We get a number density and a temperature for these H2 regions. So that concludes the section on the thermal Bremsstrahlung. Next, we have question 2, which is a planetary question. Here is the question. Again, I'm not going to read it out loud, but you can pause it if you want to read it. So the premise of this question is we have a main sequence type A star that is 50 AU away from a planet. And for this purpose, we're going to call this planet like a gas giant. Think Jupiter or Uranus. And this gas giant has a radius of r. Okay, so what is the best wavelength to observe this planet directly at? Well, let us first start by finding out what the luminosity of the star is. And so it's given that it's a type A star, but not what type of type A star. So I'm going to assume it's an A5 star, something nice in the middle. We can look at an HR diagram. Here's an HR diagram, and here's the main sequence and say, okay, here's an A5 star. And that corresponds to a luminosity of 20 solar luminosities. Okay, great. So we have a luminosity of the star. How do we use that? Here's how we use that. Essentially what we say is we can use energy conservation and say power into the planet equals power out of the planet and find the temperature of the planet. So the star is radiating isotropically. So first we have to consider the flux and not just the straight up luminosity. So it's a distance d away. And so that's just luminosity divided by this 4 pi d squared term, because we're looking at just a very small section of the sky. The next part is the cross section of the planet. And so the cross section of the planet as seen by the star is just a circle of the radius of the planet. So that's pi r squared. This 1 minus a term is the albedo of the planet. And so, like I said, we're thinking gas giants here like Jupiter, Uranus. If you look up the albedo of Jupiter and Uranus, they're about 0.3. I'm going to assume about 0.3 for this planet. And what albedo really is it's just like how reflective is the planet, because as you know, not all of the light from the star is going to get absorbed by the planet. Some of it doesn't. And so here's how you account for that. And so we take that power in and we plug it into our conservation of energy formula. And we take the Stefan-Boltzmann law and we say, okay, that's the power out. And so here we are. Here's the Stefan-Boltzmann law. Here's our power in. We can rearrange that and find T. And when we plug in all our nice numbers of 20 solar luminosities and our albedo and the Stefan-Boltzmann constant, we get a temperature of 76 Kelvin. So what can we do with that temperature? Well, we can use the Wien displacement law and find a peak wavelength for a black body at 78 Kelvin. And that is 38 microns. And so here's a handy dandy electromagnetic spectrum chart. 38 microns is going to be 10 to the negative 5 meters here. So that's in the infrared. So if we want to directly image this planet, we would want to be looking for it in the infrared. Okay, so that's nice and neat. Has anyone actually done this? Yes. So there exists a space observatory called Spitzer. Spitzer observes at 3.6, 4.5, 5.8, and 8 microns. Those are in the infrared. And so here's an example of some researchers using Spitzer data to directly image a planet. So one thing you can see immediately is they mask the center of the star. Also, you can't see the planet because the star takes up all of the luminosity, or it takes up all of the flux that Spitzer observes. So first you have to model what the star looks like, subtract that from your data, and then you can get a planet. And so these people, Martinez et al., have done that. And so here we see a planet. And it's nice and it kind of works. They're hard to see and they're very tiny, but they're able to find a planet. So good job to them, hats off. That concludes my oral exam. Thank you. Any questions?